I will drill down a bit deeper into the basic problems, and that's where I would like to begin right away. If we've got a very simple setup, that's where I would like to begin. Like, for example, one radar, one camera. Then the measurement technology to go with that has to be specifically built, not on the tier 1 that produces the camera, but basically on the level of the chip manufacturer. So if there is a Mobileye chip there, the debug opportunities of the Mobileye chip have to be specifically used so that the best or the highest data rates can be gained from the chip. Typically enough, if you take it from one supplier, then there's also a logging solution that can be easily time synchronized. You can start it well, you can stop it well. It's wonderful, a good system if I've got it from one single manufacturer. What's being measured is a multitude of data. For once it's raw data. The radar raw data or video raw data can be hundreds of megabytes per second. Then internal data, like in a Mobileye chip, the car ride results as a specific TAPI protocol or XCP protocols are on a similar level in order to get internal data from the ECU, and then the information that's still on the bus data. So as already said, it can easily be started, stopped, and synchronized. It gets more difficult if I've got two manufacturers. Manufacturer A, manufacturer B, each of them has got their own logging system. I've got two computers in the system to begin with. Synchronizing them is still possible, but it's no longer that easy. But if I move to a higher ADAS level, specifically if I've got a high equipment rate in my vehicle with millions of sensors, then I make tenders, and it may be possible that the corner radar in the front, corner radar in the back comes from different suppliers, which produces a high diversity of measurement technology solutions. So not only sensor solutions, but also measurement technology solutions, as we can see it here. Front radar, corner radars. On the corner radars, typically you need monitoring cameras looking in that direction that the radar is looking into. I need, for example, a front cam, maybe with two different resolutions of field of view, the opening angle there of the camera, with a rear cam, reverse camera, maybe a laser scanner. Then side LiDAR, Fusion ECU. If I wish to log all of that, then I've got a whole trunk full of logging solutions from each tier 1. How do I get that synchronized? I didn't write down it's impossible, but I mean, getting 1 million kilometer test data and synchronizing them is a major challenge. So we have set out to say, no matter what's happening, we set up a logging solution which is independent of tier 1s, where specifically for each chip, whether a specific radar chip, a Fusion ECU chip, it can get the maximum of data out of it. So we have gone to the start with that topic, with that system, and we're well underway. Now look at the details. What does the system consist of? It consists of 4 parts of solutions. One thing is software, scalable if possible, for most different use cases, recording only, or logging only, or also visualization. There may be something like online labeling, where I can label as I write, and analysis software. Mr. Tran presented that. So then the actual ADAS logging solution, the problem is, how can I transport 16 or 32 terabyte? That's also an issue of data logistics, because through UMTS you can certainly no longer transport these many data. Then bus interfaces, they keep increasing. We are talking about up to 20 CAN buses. Then enormous data rates created along these lines, and then specific sensor measurement technologies, sensor ADAS, Fusion ECU, measurement hardware, in order to get the maximum out of it. Let's take a look at the inside now. Let's take a look into it. What does the software look like? Our approach was we build a scalable software that also scales the hardware. If one computer is not enough, I place a second one. If that one is not enough, a third one. The goal being that one logging solution covers the basic requirements, the basic systems. So we've got the classic canopy software, where I do have XCP interfaces that I connect, or bus interfaces. This is where the entire visualization goes. But Canopy in release has got a release cycle of once a year, maybe a couple of service packs. But development is so very highly dynamic in autonomous driving that almost by the week I have to integrate new sensors. For that purpose, we have developed so-called high-performance recorders. They can be started and stopped by the main canopy. They are time synchronized, a plug-in interface where very quickly new measurement technology or new interfaces can be connected. If I wish to visualize or trigger something, then these high-performance recorders don't have any intelligence whatsoever, but they've got a backward channel into Canopy. So if I wish to trigger for measurement data from the vehicle cam, then the data would be mirrored automatically to the top into Canopy, where complex trigger calculations can run, and they would then trigger all of the recorders. In this case, I would then have a reference camera as a plug-in interface and a laser scanner LiDAR plug-in interface. So this PC would then be fully utilized, and I would like to expand my measurement technology setup for the next vehicle generation. If the CPU is not sufficient, I put in another computer connected to the first one via Ethernet, and everything is time synchronized. So in principle, it's a solution that can be scaled at random. Software gets disseminated onto all of the computers, PCs. I can expand the system quickly and integrate new sensors. The other thing that we have is time synchronization via GPS, UTC time. So if you have a platooning application in a truck, for example, where two trucks are driving, I cannot then lay an Ethernet cable. For that purpose, we use the GPS time, and we take the measurement time from the reference time of GPS, and so even two PCs that are not physically connected can be measured with synchronous times. Let's move on. The user interface is also very important. It's all new. In a few weeks, there will be the first Canopy log release. In principle, that's a Canopy which goes without a user interface, but it does have a small user interface, a mobile UI, where you can query, for example, the status of the hard disk. You can display a few individual values, but basically the user interface that a typical test driver, taxi driver, student then expected to collect data can use it. But that's not everything. This will be used in part because the vehicles are very expensive at night, in the weekend, and during the workday an engineer will go to work and he will have the full user interface. So at the left top you can see, for example, a laser scanner, point light visualization, a laser scanner sends point clouds. We can visualize them, and I can then get an object overlay into the 3D scene view, then of a radar laser scanner. Right below that, visualization of radar and camera systems going as far as GPS recording of positions and showing positions. This can be comfortably distributed to many display pages. You can do your own comprehensive visualization. It's important to know that you don't have to program it. You can have a rather simple graphical configuration with a graphical editor where I just assign then the things and the allocation is done automatically. Next thing, as I already said, you need rather many reference cameras, for example, in each radar direction. We've come up with something here where we are saying 8 webcams connected to one computer produces driver problems and generates a very high data rate. If I were to compress it to a high CPU load, maybe on the main computer, that's why we opted for a system where it take 4 cameras by way of power over Ethernet. I can connect them to a video encoder, and this video encoder is time synchronized, and then it's got a built-in H.264 compressor. So I can compress the video data up to a factor of 50. I don't have to, but I can. So we don't produce an enormous data rate based on the reference cameras only. So we are talking talking about 6 reference cams that would write 8 terabyte per day. Through a factor of 50, you can generate enormous savings. So it's always about reducing CPU load, reducing data rates, and also reducing the power consumption, because the systems then also swallow quite a lot of electricity. If I wish to use the overlay system, I need to calibrate the cameras. We have come up with a process for that. It's image-based based, so you put a chessboard in front of the camera in various positions, around 20 times, and then the camera will have been calibrated. So as a perspective then, my objects recognized by radar, by the entire sensor system, can be drawn into the video picture. And newly, we've got a kind of heat map. I can see the quality of calibration due to the actual calibration process. The target would be that the complete area should be filled, and at each place and position, as many red and green dots as possible should be shown. The red ones show far distances, green dots show close distances, trying to make sure that I've got optimum calibration, and drawing works very well. Once I've finished calibration, I can put in a test object, trying to see whether the calibration works in a clean and good way. Let's go on. Something that I mentioned earlier, labeling. There's the opportunity for offline labeling, of course. Typically enough, in low-cost countries like India, many people will be sitting there, typing, taking a look at the videos and labeling them. Another option that we offer is to use a canopy panel to do online labeling. Quite often there are 2 drivers on board. One of them drives the vehicle, the other one is the operator. And here we've got a panel with up to 50 situations. So one driver presses what you've seen under a bridge, over a bridge, and then I set my labels. And the interesting thing is that later on, by way of data mining, I can run search functions for the labels and pick out those places where I want to do more accurate analysis. Which brings me to my very next topic, data analysis software, vector measurement data system, which is available in 2 ways. So you can do it in a cloud for once. Certainly not all of the raw data would be put into the cloud, but rather the object data and signal data. But you can also do it on-premise on an existing server. And then accordingly in pre-processing, the tags would already be set so that I analyze only the data that have been recorded at night and so on and so forth. So there's a complete management system to go with that. This is also comparatively new from Vector. This is the actual data analysis, data mining workflow. Either you can program your own functions, or you can use our programming library with almost 100 options there. I can select them, chain them up, I press start, and then it analyzes an entire row of test data fully automatically, finding the hits, when did we have a certain condition, and for each of those conditions a report can be generated, and this report can have an object overlaid video function. I could say search everywhere where I've got a parsing process, where I've got a line that I'm not allowed to cross, where I'm crossing it and see the driving behavior that an automated vehicle wouldn't have been allowed to do. So programming is very easy. You can do it at random. A multitude of functions can be coupled up in order to do data mining of this type. Let's take a step on to hardware. The central computer that it all runs on is a brick system. Currently, it can log up to 10 gigabits per second. Very soon, there will be an update to 16 gigabits. So main connection 2 times 10 gigabit lines. So with 1 gigabit Ethernet, I can't get far anymore. And there is a takeout storage rate where I can place up to 32 terabyte disks, and then optional, for example, 2 times PCIe extensions where I can add additional channels. What we are still developing is a slightly smaller one, which can log up to 4 gigabits. That's more for single sensor systems and for automotive Ethernet applications. That will be coming forward in roughly half a year, 9 months' time. Let's go on to data logistics. I said 32 terabytes or 16 terabytes after one test drive. Transporting them to the computing center amounts to a challenge. The way that is available at the moment is comparatively simple. You move out the hard disk from the vehicle. If I were to log with 500 megabyte, for example, if I were to read out with 500 megabyte, then if I drive 5 hours, I have to read out for 5 hours. So if I come back, I would have to provide power for the vehicle for 5 hours, or power the computer for 5 hours to read the information out. So you can therefore just simply take the storage system, play it into a docking station, and the docking station copies it into a drive, and I send it from there to the data center. Alternatively, if we are working on an entire copy station, I put it in, I press one button, and then scripts are running in the background that can also do video compression, so that at 10 gigabit it can be played right into the data center. On to bus interfaces. I think this is sufficiently known that Vector has got automotive Ethernet bus interfaces up to 12 channels, currently connected with USB 3.0. This is a very multifunctional device, but it's not up for maximum performance. What's being developed here by us is a new device which can be connected with 10 gigabits, and especially the combination of this device and the small brick represents a highly performant Ethernet logging system. It fits right on top of another, and 24 channels with 1000 base T1 can then be transmitted to the computer. On to the fusion ECUs, measurement technology. Here again, I can give only isolated examples. This is one where I've got a setup of an Infineon, for example, with an NVIDIA or an Intel processor. Of course, the ECU can be measured via Ethernet, but the measurement bandwidth is rather limited. So maybe we are talking about 10, 15 megabyte that we can measure through Ethernet. There are requirements from the Infineon of measuring 50 megabyte, from Intel maybe also 50 to 100 megabyte. So with these kinds of requirements, it gets very difficult. We've got a specific measurement technology that adapts high-speed interfaces, for example, Infineon via Aurora and Intel or NVIDIA via PCI Express. So that goes out via one line. You could add CAN FlexRay, and then with one cable, all the information goes on to one canopy system. Another example, maybe one very interesting point here. First of all, we said earlier that AUTOSAR Adaptive is about to come. And from then, there will no longer be any static linking. The classical XCP functionality, where in one specific place I find a signal, does no longer exist. It's no longer there. That's why we came up with a so-called DAS concept. If it's dynamic to the compile side, static to the runtime, then this hardware can smoothen things in such a way that any normal tool can be connected behind it, although up front at the compile time, the address allocation is dynamic. Of course, this goes into measurement technology and adaptive AUTOSAR stack with the appropriate processors, which then at random, as it were, can link the signals elsewhere. Let's move on to radar measurement technology. It's completely different according to the radar microcontroller being used. I, for example, took one from Infineon. If you were to take an LXP, which is also very widespread, it would be completely different. What we've got is like with the Fusion ECU, we measure Aurora. So what's happening in the CPUs via the classical Aurora interface with up to 50 megabyte per second. So we get the FFT results, the classification, detection, and then there is a second path where the raw data interface is directly tapped, and we measure the raw data. And this, once again, can be done with one cable. It goes into a box, is edited, and then is transported onto Canopy. The hardware integration is very sophisticated there, measurement technology and radar, because the radar is very small, and additionally energy input, it's very sophisticated. So you need to take a very close look as to how can integrate our measurement technology into this radar. Finally, as a measurement technology, I want to present a video raw data solution. Mobileye, I can't understand it, I can't prove it, but it's being said that they've got a higher market share than 50%. I think this might be more or less right. The setup is always very similar. I've got a camera imager sending the video raw data to the Mobileye chip. The Mobileye chip configures beforehand what the camera imager is expected to do. Pixel rate, frame rate will be configured earlier. The output from the Mobileye chip is an SPI connection that goes into a microcontroller, where the objects then are passed on as CAN or automotive Ethernet to the other control units. So classically at the end, I can measure CAN FD or automotive Ethernet, but that's far from sufficient for a complex video logging solution. In order to get that, I need to tap the debug data of the chip and the video raw data. For that purpose, you use a MIPI bridge, where you can extend the raw data by way of a serializer, a so-called FPD Link 3 interface. You can get the video data out. 5 meters is not an issue. Then you can install a video grabber and then put it into the computer with 10 gigabit. And the TAPI data are rather complex debug data. With a mobile iLib, you have to get everything integrated. Then there is also online validation. So whether the optimized data fit with the debug data, and only if it's all in a good fit, only then will things be recorded. So all of this is available from us. And that's the end of my presentation now, with the exception of one particular feature. I have presented so far rather many individual boxes, separate boxes. And if you think we are going in the direction of level 4, this was more than level 3 setups, and it gets more. And who wishes to place 10 boxes in a vehicle? So with high pressure, we are doing development work on the so-called 1161, a modular system with 6 interface modules. So I can put in POD video bus interface, and especially in connection with the new automotive Ethernet interfaces of the PC, I can then set up rather compact system, as shown at the bottom, for example, 24 automotive Ethernet interfaces, radar, video, and the like. And I need to pull out only just 3 cables in order to put it into one network. Thanks for the attention. I whipped it through rather quickly because I knew I wouldn't be able to stay within my time limit.